and we're going to pick up where we left off. So we got pretty far along here in terms of this first membranes packet. So really talking about the forces that are acting to move particles across our cell membranes. And so we describe those two forces. And can anyone just quickly in the chat as a review here or recall, what was the chemical driving force based on? What did we say the chemical driving force was based on?
The charge in and outside of the cell.
So not the charge, right? So we're talking about the chemical driving force. So that first force.
Was it the going from high to low concentration?
Yes, excellent, perfect, thank you. So it's going to be based on the concentration gradient. Perfect, I'm also seeing that in the chat here. So yes, the concentration gradient is what determines the chemical driving force, right? So based upon, you know, what the proportion of those molecules are, if there's more in one area, less in another area, that is the force that wants to bring particles to equilibrium. And so that's the force that wants to move those particles across our membrane to balance them out, their concentration. The electrical force, which is the second force, is what was mentioned at first. Okay, so that is based on the charge. So the electrical driving force, we said, was based on two things. One, the type of charge on that particle, right? Whether it's a positive charge, negative charge, divalent, monovalent. And then the second factor that determined the electrical driving force was the polarity of the cell. The fact that we have an uneven distribution of charge, the fact that there's more negative inside and more positive outside. And so that polarity is the second factor that determines this force. In other words, particles want to move. If they're positively charged, they want to get to the internal negative environment of the cell. If they're negatively charged, they want to get to the external positive environment, and so on. If they're divalent, it's going to be a stronger charge than if they're monovalent, etc. Okay, so those were our two separate forces, and we began kind of combining those forces and then determining what does the overall movement of this particle look like if there are two forces acting on said particle? And we kind of said that, if we jump back here, if both of the forces were acting in one direction, it was pretty straightforward, right? We just add those forces together and the net direction, the net movement of that particle will be in favor of that force. But things get a little bit more tricky if the forces are acting in separate directions, okay, in different directions. And so we spoke about the equilibrium potential because we're going to need to find out what the equilibrium potential is for this particle, for this ion. And then that will determine which is the stronger force, okay? That will determine what the overall net direction is if the forces are acting in different directions. So we described the equilibrium potential, and just to review that, we said that it was the membrane potential, so it is a membrane potential value. It's the membrane potential at which the particles are at equilibrium. In other words, it's the membrane potential at which the electrical driving force is equal and opposite to the chemical driving force, okay? And so the net directional movement is 0. And it's going to be different for different ions. For potassium, it's -94. In other words, when the cell membrane potential is -94, potassium does not move. Its chemical driving force is equal and opposite to its electrical driving force. And so what this relationship shows is that the equilibrium potential is really a determinant of the chemical driving force, whereas the membrane potential is really a determinant of the electrical driving force. Okay, I'll say that again. The equilibrium potential is really an expression or determines the chemical, is determined by the chemical driving force, and the membrane potential is determined by the electrical driving force. Okay, so that's going to be really important in terms of what we're going to illustrate here now. Jesus. Okay, I apologize here. I don't know why this is not cooperating. Okay. So let's illustrate what happens when we have different scenarios in terms of those different driving forces, and we're combining those forces. Okay, so now we're determining the direction of the combined force. So this is determining the direction of the electrochemical driving force. In other words, our ECDF. Remember, this is the combined sum of both of those forces. So electro and chemical gives us the electrochemical driving force. So what happens when we combine those forces, and how do we determine the overall net direction of those particles? So first thing we want to do is we want to identify the direction of the separate forces. So we identify, oops, and I can't spell today. Okay. We identify the direction of the individual forces. So the chemical driving force and the electrical driving force. That's the first thing we do. Okay, is it going into the cell, out of the cell? And we do so for them individually. The next thing we do is we will have three different scenarios here, or rather two different scenarios. So the first scenario is that both of these forces, the chemical driving force and the electrical driving force, are in the same direction. Okay, so if the electrical driving force and the chemical driving force are in the same direction. That's pretty straightforward, right? Then the ECDF, so the combined force, is going to be in that same direction. Okay, so we have two forces, they're both in one direction, and then we just combine those forces and they're both in the same direction. Let's look at what happens if they are in different directions. So what happens if EDF and CDF are in different or opposite directions? Okay, now what we'll do is we're going to compare the equilibrium potential and the membrane potential. So we're going to look at those values, and that will tell us which is the stronger force. Okay, so if the forces are in opposite directions, we compare, oops, just trying to get red here. We compare the equilibrium potential of the ion, whatever that is, so EX, X representing said ion, versus the membrane potential of the cell at that time, okay? Now, if the equilibrium potential is greater, that's gonna favor the chemical driving force. If the membrane potential is greater, that's going to favor the electrical driving force, okay? All right, so let's think about what happens with our three different scenarios based upon this relationship. So if the equilibrium potential is greater than the membrane potential, right, we're looking at our two values now. So we're looking at the equilibrium potential of the ion in question. We're looking at the membrane potential of the cell at that time. If the equilibrium potential is greater than the membrane potential, so this is our first scenario here. So if the equilibrium potential is greater than the membrane potential, then our chemical driving force is stronger than our electrical driving force, right? Then chemical driving force is stronger than electrical driving force. And then the ECDF, the combined forces, will follow the chemical driving force. Okay. The second scenario is if they're equal and opposite, right? If the equilibrium potential is the same number, if it's the same value as the membrane potential, and we kind of talked about what would happen in that scenario. So if the equilibrium potential is the exact same and opposite, right? Because that's what we're dealing with here. If it's the same and the opposite as the membrane potential, then the chemical driving force is equal to the electrical driving force, and none is stronger, so to speak, okay? Then the chemical driving force is equal to the electrical driving force. And we can say that the ECDF is equal to 0. In other words, no net movement. Right? We're at equilibrium. Oops, I can't spell today. This should be 1L. Equilibrium, all right? If the membrane potential is now greater than the equilibrium potential, now we're going to see the opposite is true, right? The electrical driving force is greater than the chemical driving force. So if the membrane potential is greater than the equilibrium potential, then the electrical driving force is greater than the chemical driving force. And the ECDF, which is the combined sum of both those forces, will follow the electrical driving force, okay? So hopefully we can see how this relationship holds true, right? The equilibrium potential is indicative of the chemical driving force. The membrane potential is indicative of the electrical driving force. And so if we have forces acting in opposite directions, then we simply look at these values to see which of the forces is stronger. If the equilibrium potential is a stronger value, and it's greater than the membrane potential, then the chemical driving force is the stronger force. And so the overall movement of that particle will favor or follow the chemical driving force, the direction of that force. If they're equal, right, so if they're now opposite and equal, then those two forces simply net out, okay? And this we know is true. If the membrane potential is the same as the equilibrium potential, then the particle is at equilibrium. And so there's no net movement as the chemical and electrical driving forces are kind of netting each other out. They're the same value and they're in opposite directions. If the membrane potential is now greater than the equilibrium potential, now because the membrane potential is indicative of that electrical driving force, the electrical driving force is the stronger force. And so the overall movement of said particle will follow or favor the direction of the electrical driving force, okay? And so this is how we can determine, although we've got different forces acting on particles, what the net direction, what the net movement of those particles will look like if the forces are in opposite directions. We simply look at the equilibrium potential and the membrane potential, and then deduce the direction of the stronger force from that, okay? All right, any questions here before we keep moving? Okay. Okay. And so if we look at this scenario here, this is a really good example of looking at that relationship. So on the left, what we see is the membrane potential is weaker or smaller than the equilibrium potential. We can also see that at the bottom here, the equilibrium potential for potassium we described as being -94. The membrane potential for a resting cell is -70. And so looking at these two values, we know that the equilibrium potential is the bigger value here. In other words, the chemical driving force is the stronger force. And so the chemical driving force is moving potassium out of the cell. The electrical driving force wants to move potassium into the cell, but based upon what we just described and based upon the chemical driving force being stronger of the two, then the net direction of the electrochemical driving force will favor the net direction of the chemical driving force, and that will be out of the cell, okay? And in terms of the value of that force now, we simply subtract electrical from chemical, and we can appreciate that that's going to be a smaller value. Because they're in opposite direction, we subtract the weaker force from the stronger force, and so it's a smaller value in the net direction of the stronger force. On the right, or this illustration C here, we'll see the opposite relationship, so the opposite of that. This is what happens if the membrane potential is stronger than the equilibrium potential, okay? And so we can see that again at the bottom here. The equilibrium potential, again, -94 for potassium. The membrane potential at this time, right, the state of the cell at this time is a membrane potential of -100 millivolts. And so the membrane potential is now stronger than the equilibrium potential. And so while we have two forces moving potassium in opposite directions, the net direction will favor the direction of the stronger force, which is the electrical driving force, because that is indicative of the stronger value, which is the membrane potential, okay? And so the net direction in this scenario will be into the cell. So once again, we subtract the weaker force, which is the chemical driving force, from the electrical driving force, and we get the value of that force, but then the direction is going to be in favor of the stronger of the two, which is the electrical driving force.